The next in our series of heat calculations talks about Gibbs free energy. And I use the Gibbs not so much because I want to give credit for who did it, but because it helps you remember the symbol that's associated with it. And that's delta G. So we're going to be measuring the change in the Gibbs free energy. Now when we talk about free energy, we need to understand what free energy is. Free energy is the energy that is available to do work. There's a lot of energy associated with these bonds. A lot of the chemicals that are held together require a tremendous amount of energy to keep them in place. So these are all tied up in those bonds and therefore can't do work. It's the leftover energy that we're referring to. So when we refer to free energy, what it translates into is the spontaneity of the system. Will a reaction take place without any outside intervention or not? A positive delta H value means it is non-spontaneous, meaning a jump start of energy is going to be required in order to make that reaction go. However, a negative delta G value means that there's enough energy that's just inherent in the area to cause it to go. So this will be a spontaneous reaction. Delta G is calculated using delta H and delta S. So really delta G isn't using anything new other than the answers that we already have. So for the most part, we want to know about what is spontaneous at room temperature. At room temperature is 25 degrees Celsius. Remember back when we translated from Celsius to temperature, or to Kelvin, we added 273. So we're talking about 298 Kelvin. So the equation that we're going to use in order to calculate delta G and thus determine our spontaneity is delta H minus T delta S. And there is a trick associated with this. Now looking at this equation here, we could look up values, we could calculate delta H. For simplicity's sake and to save us a little bit of time, I'll go ahead and calculate that for us. Delta H's value is negative 104.215 kilojoules. Delta S's value for this particular equation is 85.54 joules per Kelvin. Hopefully you can see the issue with this before we proceed. Maybe you have, maybe you haven't, but the major issue with this is that we have to have the correct units in order to subtract these. Alright, so let's go ahead and change this over into a unit that we can use. So first and foremost, here we go. Delta G is going to be equal to delta H, but we're going to translate it into joules. So that's negative 104,215 minus the product of T, 298 Kelvin, times S, delta S, 85.54 joules per Kelvin. When we multiply these values together, we get that the parenthesis area is negative 25, it's minus 25,490.92 joules. And the Kelvin cancels out. When we take this negative value here and subtract this value here, this negative is the one that's here, we get that our delta G is equal to negative 129.70592 kilojoules. Because our value for delta G is a negative value, this is a spontaneous reaction and will take place all on its own. This is an introduction to Gibbs free energy and how we're going to use it to be doing our calculations in class.